Okay, so just now I just got stuck a bit. So actually this term here should be sine of theta out rather than cosine of theta out. So yeah. So actually if it is a sine of theta out, so here it should be sine of theta out equals n1 over square root of n1 square plus n2 square. Rather than this is cosine, then feel like theta out and theta b should be the same. But here, if it is correct, and here sine of theta out should be n1 over square root of n1 square plus n2 square, which means that theta out should be this angle. Theta out should be this angle. This is n1 over this square root of n1 square plus n2 square. So in this right angle triangle, you can clearly see that theta b plus theta out is 90 degree, and actually this is theta b, this is theta out, and of course this is 180 degree. So this angle should be 180 degree minus theta b minus theta out is 90 degree. Okay, so and of course still theta b plus theta out is 90 degree. This is 180 degree minus it. So yeah, the remaining is still 90 degree. So we have used this equation for the Brewster angle to verify this property. Actually, I think in the past exam I have asked a similar question before. So here, before we end chapter 32, we have a couple of additional example. So the first one is also related to the polarizing filter. So here it says a polarized light is sent into a system of 3 polarizing sheets. The angle theta 1, theta 2, and theta 3 of the polarizing direction are measured counterclockwise from the positive direction of the y-axis. They are not drawn to scale. So angle theta 1 and theta 3 are fixed. Okay, so the angle for the first one and the third one cannot change at all. Okay, but angle 2 can be varied. The intensity of the light emerges from sheet 3 as the function of theta 2. The scale of the intensity axis is not indicated. What percentage of the light is initially intensity is transmitted by the system when theta 2 is 30 degree. Okay, it asks you what is the percentage of the lights can go through this 3 filter system if theta 2 is 30 degree. So far theta 1 and theta 3 are fixed, but we do not know what are theta 1 and theta 3 yet. So the first thing we need to determine what is the value, what are the values of theta 1 and theta 3. Okay, so we don't have too much information. The only information is this figure. So we should be able to find some clues about the value of theta 1 and theta 3. Okay, so actually this is peak at this angle, and this is theta 2. This is theta 2. And some interesting point should be 0. Interesting point should be 0. Yeah, based on this point, we might be able to really find theta 1 or theta 3. Okay, so when I equals 0, then we can observe that theta 2 is 0 degree, 90 degree, 180 degree, at least for this 3 angle. Which means that, so at the very beginning, theta 1 is unpolarized. And then after going through theta 1, we do not know this angle, but at least it is polarized. after going through the first filter. And then for the second filter, if it is 0 or 90 degree or 180 degree, it makes there is no light can go through. But as much as we know, we should have something like I2 equals, or maybe I prime equals I0 cosine square of theta. And when is cosine of theta is 0, is actually like theta equals 90 degree, theta equals 90 degree. Which means that the angle between theta 1 and theta 2, let's say theta 2 minus theta 1 should be like 90 degree, or theta 2 minus theta 3 should be also 90 degree. Let's say if it is this one, of this case, theta 2 is 0 degree, which means that either theta 1 or theta 3 should be 90 degree. So at least theta 1 or theta 3 should be 90 degree to make this point to be 0, to make this point to be 0. And then the next thing is, if one of it is 90 degree, then it does not enough, because we still need this point to be 0 degree. If this point need to be 0 degree, then that means that theta 1 or theta 3 should also be 180 degree or 0 degree. But this is actually the same thing. So maybe you just let it to be 90 degree. Okay, so in this case, we know, based on this observation, we know as much as I to be 0 when theta 2 is 0 and 90 degree, which means that theta 1 or theta 3 should be, this one should be 0 degree. Should be, one of it should be not 0 degree, one of it should be 90 degree. So here, we can say without loss of generality, we can let theta 1 to be 0 degree and then theta 3 to be 90 degree. Yeah, because one of it is 0 degree, one of it is 90 degree. Okay, if you don't believe, you can just try to assume theta 1 to be 90 degree and theta 3 to be 0 degree. Then the answer will still be the same. Okay, so here we make this assumption, so we can just find, okay, so let's say this is IF, and maybe this is I1, this is I2. Okay, so this is I0. Okay, so here we have a 1/2 factor. Okay, and this is 0 degree. This is here we have a theta 2 to be 30 degree. Okay, so here we should multiply it by cosine square of 30 degree. And then from here to here, this is theta 3 is 90 degree. So we have a 60 degree between them, which means that we need to also multiply by cosine square of 60 degree, which means that for IF should be I0 times, the first is 1/2 for the first filter, and then the second filter is a cosine square of 30 degree, and then for the third filter is cosine square of 60 degree. So we have I0, or maybe you can directly write it as 9.4%, which is actually the same as the previous sample problem. But here it just asks you what is the value like here, somewhere like here. Like this. Okay, so next we still have another sample problem. Okay, so it asks a certain helium-9 laser emits red light in a narrow band of wavelength centered at this frequency, 632.8 nanometer, and with a wavelength width of this 0.01 nanometer. So what is the corresponding frequency width for the emission? Maybe you don't know, or what does it mean by wavelength width? What does it mean by frequency width? Okay, so let me try to explain this way. So practically, when we try to generating something with a fixed frequency, we may have difficulty to do so. Just like when you try to generate a sinusoidal wave, there may be some frequency variation. Suppose this is a sine wave. You try to generate a sine wave. Yeah, but in the real world, there will be something like the noise. Okay, so it makes things the frequency of this sine wave might not be so accurate, which means if we try to consider what is the period of a sine wave, we will try to count. Okay, so this is the time that it crossed the 0 point, and then let me try to count another point that try to the time point that also crosses 0 point. Okay, then this is the period. But as much as there will be some noise, then for every period, this time might be a little bit different. Which means that as much as we should have something like F equals 1/t. If this thing vary a little bit, then it means that the F will also vary a little bit. Okay, so it means that if we try to, for example, we try to do the statistic of the period. We try to do the statistic of the period. Let me count. This time it is just say I'm not sure what is the number, but let's say if every time it has a different period, then it refers to a different frequency. Then we can try to draw out the histogram. In Chinese it's called 直方图. Then we may be able to try to draw. Okay, so most of the time this is the wavelength lambda, and then for some time it may be not so accurate. Okay, and the histogram might be something like this. Okay, which is like a Gaussian distribution. Okay, so here we try to quantify it. It may go for a very large gap. If you really need to count, what is the range that the histogram is within this range, then it may go to a very large far away. So let's try to count if it is the top, and then let's try to count what is only half of it. Okay, so this is the peak, and then let's try to go for the half, and then this width, we can really evaluate this width. In statistics, we will try to call it the standard deviation. Actually, not really the standard deviation, but in physics we may try to count it like this, So this is the peak distribution, and then we try to count what is the half magnitude. Like a 3 dB point. Okay, so reduced by half, And then let's try to count this width. Okay, so this is the delta lambda. Okay, so this number, if this number is smaller, which means that the frequency is more accurate. Okay, so here it means that, okay, we have the wavelength. The wavelength itself, so this point is 632.8 nanometer. And then it tells you that the delta lambda, it can be half of it or maybe full of it, just depend on how do you count it. Maybe you can just count by, maybe you can just count by half of it. Okay, so maybe this is the delta lambda. Delta lambda is 0.01 nanometer. And then what is its frequency width? Of course, if you don't try to use the calculus, you can just say, okay, for this point, this is 632.8 nanometer. And then we can also use C equals F lambda to calculate things out. We just need to plug in C is 3 times 10 to the 8th power. And then wavelength 632. And then we plug in 632.8 nanometer there. Of course, nano is 10 to the negative 9. Okay, and then you can find out what is the frequency correspond to this point. And then you can just subtract the width, 0.01 nanometer there. Okay, so this is 632.8 nanometer minus 0.01 nanometer. Then you can know the wavelength of this point, and then you notice the wavelength of this point, and then you plug in here. Then this is 632.8 minus 0.01 nanometer, and then you can calculate the frequency. Then you can know what is the corresponding frequency of this point and what is the corresponding frequency of this point, and then you subtract them. Then you can know the so-called frequency width. Okay, and then you can correspond to what the x-axis is a frequency, and then it is still another Gaussian distribution. And as you know, F and lambda are inversely proportional. If delta lambda is smaller, and in the frequency it will be large. It'll be large. Okay. No, not really. It is still, it is proportional to each other. It's still proportional to each other. Okay, so actually we can still make use of F, C equals F lambda to really calculate the delta F, but we can make use of the calculus rather than doing this thing. Okay, so this is 632.8 minus 0.01 nanometer, and then you can plug in there. Here we try to take derivative, but before we take derivative, we can just try to rearrange the equation like F equals C over lambda. F equals C over lambda. Okay, so on the left side, F is a function. F is an independent variable. Lambda is another independent variable. C is a constant. C is the speed of light. Okay, so here we can try to take the differential on both sides, which means that on the left side it is df, and then on the right side, take the derivative. C is a constant, so C remains there. And then this is like C times lambda to the negative 1 power. Okay, this is a polynomial. Okay, negative 1, so it becomes lambda square. And then we need to multiply by this negative 1, so we have a negative sign. And then we have d lambda. Or if you don't familiar with it, you can regard it as a df d lambda. So f is actually these things. Then you can have a d lambda and then c over lambda. and then here we have c negative over lambda squared, and then you move this one to the right side, then this is this thing. Okay, so here when we consider frequency width, we don't really care about whether it is positive or negative. So we can just take the absolute value df equals c over lambda squared and then d lambda. So here we can just plug in 3 times 10 to the 8th power over lambda is this one. So this is 632.8 times 10 to negative 9. And then here we have square. And then the wavelength width is 0.01 times 10 to negative 9. So this number is 7.49 gigahertz. So in that case, suppose we have this is the Gaussian distribution. Okay, here we try to count for the half of it. Okay, so this is the delta f. This is the delta f. And you know, as much as f and lambda are inversely proportional, which means that if you have a higher frequency, it will, if you have a longer wavelength, it will correspond to a shorter frequency. That's why here we have a negative sign. But at least you know, if we have a wavelength width of 0.01 nanometer, then the delta f will be 7.49 gigahertz. Okay, it seems very large, but actually not, because when we consider the visible light, visible light is somewhere here. The frequency is like something times 10 to the 14 power hertz. Okay, so if it is just varied by 7.9 gigahertz, so this is quite small, it's quite narrow within this frequency for the visible light. Okay, so this is 10 to the 14 power. And here the variation of the frequency is only 7.49 gigahertz. Okay, so